Alrighty, I guess I'll go ahead and get started here. My name is Travis, and I'm going to be talking about compile time scaffolding in Scala with GADTs. We're going to kind of just go into some GADT basics. What are they? We're going to add HList to our GADT. We're going to do some validation. We're going to talk about validation in the context of GADTs. Talk about describing REST endpoints, a little demo, and then we'll end. So the objectives today are to learn about GADTs and interpreters. They're pretty easy pattern, and they can help reduce a lot of boilerplate. So what I'm presenting is kind of how I derived a project I call Bones. Like I said, the goal is to cut down on boilerplate. And another thing is if you saw the Scala Z schema, who I guess is now Schema Z, we're kind of have the same problem domain, and whatever I'm showing here, you can utilize their project to kind of do the same thing. So depending on which approach you would like to take, yeah, that'd be cool. So, all right. So scaffolding, I kind of hijacked this term from Ruby, but if you don't know what that is, it's basically just like auto-generation of the model view controllers, and in Scala I'm kind of trying to talk about basically auto-generating type classes and functions so that you can build a REST services. And GADT stands for Generalized Abstract Data Types. So let's get into this. If this looks familiar if you're at the Schema Z talk. We're going to start by defining a base class, which is our KBP value class, and it's going to have this type parameter A. And A is not actually used in the context of KBP value. We have 4 subtypes. So our primitive data, string data, and double data, they know something about the data, so they can fill in the type parameter with the data they know about. So for instance, string and double. Our optional data is going to be a wrapper, a recursive wrapper of a KBP value. And so that it's wrapping a KBP value of type B, so then it can fill in the type as an option of B. And then finally, we'll look at the tuple data. It actually recursively wraps 2 elements, and the resulting type is a tuple of the element 1 and element 2 of the tuple. Okay, and so to actually kind of start building up your data structure, we can do this, and notice the KBP value type is being reflected as the type that is being built up here. So we're going to wrap this in option, and so now we have the KBP value of option of tuple of double. We'll add a what do we add? We added a double at the end of that, an optional double at the end of that, and then finally we added a string to the beginning of that. So then, but our type, our compiler actually keeps track of this type. We don't actually have to write this out every time, but the compiler is going to keep track of this for us. Okay, so I'm going to give an example of parsing key value pairs into JSON. Okay, so we're going to define the keys as on our primitive types. That's the only difference here. We're now going to build up our schema. So our schema, now we're adding names to these things. So a string, which is a name, our 2 doubles, our latitude and longitude, and then the height is a double as well. Okay, and this is kind of a representation of what our data structure looks like, with the leaves being our primitive values, and the top being, the wrapped up type that we talked about. All right, so Here we are, once again, defining our schema, this time with the parameters. And so then we are going to provide an interpreter. When we come across, all right, so this is a pattern matching, and so we're going to pattern match on each subtype of KPP value. So when we run across a tuple data, we are going to recursively call create data to get the documentation of the element 1. We're going to recursively call to get the documentation of element 2, and then we're going to combine those together with the metadata combined with. Right? For optional data, we are essentially going to do the same thing. We're going to recursively call to get the description of the wrapped type, and then we're going to add some metadata that says which this is awesome, and then finally when we get to our primitives, we're just going to print out string with a key. Okay? And so when we, let's see, when we pass our schema to this interpreter, it is going to print out the type there, or the description of the data type that we have. And if you wanted to do this as a type class, this is probably show of A, which would be kind of a different way to do it. Okay, and then graphically, or so what we're going to do is we end up actually creating another data structure here with the types, with the descriptions filled in, and so we recurse down to our primitives, and now we're rolling back up into finally our complete result. So we just generated documentations describing our data. So, all right. So now we're going to talk about marshalling this JSON data. Right. So we're going to create another interpreter to marshal. So the result type of this is going to be of type A to JSON. And so if you remember, our schema has that big long, the string double type. So we're going to create a function that goes from the string double to JSON. And so first, we're going to pattern match, and we're going to find our primitives. When we get to our primitives, we're going to create a JSON object that just has one element in it, and then use the key and the value. And so you can see that if this was just a string data, if A was just of type string, we would have a function from string to a JSON object. Okay, and so those would be the leafs of our nodes there. So now we're going to pattern match on optional data. So the first step is we're going to recursively call this toJSON function with the wrapped KPP value type. And as you can see, this is our type B to JSON. And then we're going to create a function. And we know it's an option of type B because that's what option data declared the type to be. And we can match on that. And now in the none case, we return an empty JSON object. And on the sum type, we recursively call to marshal the contained data. The contained KPP value. Yep. So that would be filling in. That's where the option types were right there, or the option data. Okay. And then finally, there's the tuple type. So first, we recursively call to get our function from E1 to JSON, and then E2 to JSON, and then we can create this function where we call those functions and then combine the result. And that combine just takes two JSON objects and combines them into a single JSON object. Okay. And so then that fills in the rest of our tree. And then the resulting type, of course, is a string of double, double, double to JSON. Okay. Everybody good so far? All right. So now we are going to, what are we going to do? Oh, we're going to create, first we have to create our function here. So here's our waterfall schema. We're going to pass it to our JSON function, and that returns us our function that we just talked about. Now we're creating some actual data, so that data type right there is our string double, double, double. And now we pass it to our function, and then we get our JSON object. So, right. And this represents the JSON object at each element of the node, it starts building up at the leaves and then goes upward. So now we can generate JSON in documentation for any combination of tuple, option, string, and double. Okay. So quickly going to go through the unmarshal example. The difference here, of course, is we're going from JSON to either a string or a string or an A, where the string is just going to be an error. So if there's an error, we're going to return it as a string. Okay, and so we match our string data. If we can extract the data, we return it. And if we don't get an error for optional data, we once again are going to recursively call to get the function from JSON to either B, and then unmarshal that. And then finally, we match on the tuple data, recursively call to get the function from E1, from JSON to E1, and then JSON to E2. And then we can run those functions. Create a function, return that that's going to be returned, and here we are extracting the data and then combining the tuples together. So here is the representation at each leaf of the node again. At each node starting at the leaves to where we finally build up the type at the top, which is JSON to an either or to our JSON of either an error message or the string double, double, double type of data. Sorry. And so now we can create our function from JSON to our A type and pass in the JSON we just created, and you can see our resulting type is a write, because it succeeded, of our original. Right? So that's how that's built up again, starting at the leaf nodes and then working its way up, combining the data along the way. Okay, so now we can generate documentation, we can parse JSON, and we can generate JSON for any combination of tuple, option, string, and double. All right. So we're going to improve this a little bit, and we're going to use HList. The current implementation does not allow for hierarchical data. Tuples are a bit clunky, and HLists are associative, so depending on how you build up your tuple, they could be nested in different ways. Where in HList, as you build it up, it is uniform. And we do want to be able to represent hierarchical case classes like this location and this waterfall class. And so just a quick overview of Shapeless, if you're not familiar with it. Let's see, it can, okay, so here's a representation. The top is just the tuple data. And then the bottom is how you would represent that is an HList. And what it is you start with the HNIL on the right side, and you prepend elements one by one to the to the existing H list, kind of like you would do with a regular list, and then you build up the type. So this type is still string, double, double, double. But there you can see that the HNIL in the nested type, there is an HNIL in the nested type because that's a separate list. And then you can see the HNIL at the end of the entire type. So, okay. Nice thing about HList is we can concatenate HList of our arbitrary sizes. So this is like our product types. So the double colon is a cons. Obviously, you're just appending or prepending one type, but the triple colon allows you to prepend or concatenate two H lists together. So, okay, and then it actually allows us to arbitrarily split an H list. And this is not only at the implementation level, but actually also at the type level. It'll actually keep track of all our types for us. So here we have a split. So we have our data type, and then we're splitting on the 2, because the natural number of 2 at the very end there, and it creates a function from our H list to a tuple of H lists, and we can call split, and it splits it up for us. And so that's going to be important for our interpreters for H list. So also it provides a coproduct, and I actually did not get ever to implement this in the Bones library, but this would allow for us to do some types. Okay, and HList does allow us what it does is it automatically generates functions to and from our HList class to our case classes. So by calling this generic, I think this is a macro of sorts, but if you call generic location, this gen location or this gen waterfall is now, you can see the first one, there's a function called to, which is a function from our waterfall to our H list, and then the from is going to be from our H list to our waterfall. So, okay, so some positives for H list is split and concatenated or provided by Shapeless, so we don't have to worry about coding it. These can be captured implicitly when building our GADT structures, and they're associative. Our H list is really kind of difficult with pattern matching. There are some workarounds that are not very pretty right now. For instance, I'm using an as instance of H in a few areas where, for some reason, the Scala compiler can't quite figure it out. There's people call this, I think, a Scala golem or something, or Scolem. GADT Scolem. I think it can be hard to work with in Scala. So we're going to refactor our KBV value, and I'm not going to show you any code. I'm just going to kind of generally tell you the improvements for this. So we actually break our base class into actually two separate algebras. So this is a little bit different than the Schema Z, how they actually did this. They actually used type parameters, type classes. This is kind of allowing us to, you don't always need to represent, or you don't always need to name your JSON values. For instance, like a list of values. This will allow us to not have to name that. All right, so what we're going to do here is we introduce this new KBP H-list, and so that's going to represent basically the list of data. So this is going to allow us to group 0 or more key value pairs. So you can think of this as kind of the object. And we're going to mirror H-list. We're going to introduce a new class, which is this key value definition. That's where we're actually going to store the key. We are going to keep it as a string. And that's going to have a reference to our original KVP value GADT. And so this second KBP value, this is what we showed earlier, but we're going to remove the tuple type, and we're going to add this new class, which is now a representation of converting the H list to the case class. Okay, and because we have two algebras, we now are going to have two interpreters that will recursively call each other. And this is called mutual recursion. So this KBP convert data is what I was talking about. So it has a reference to our other type, which is our KBP H list. So now we have 3 type parameters on this KBP convert data. The H maintains the H list. The N is going to maintain the size of the H list, and then A is going to be our case class. And I think this Schema Z did this with ISO, because as I've learned, this is an isomorphism, and so we have an H to an A, and then we have an A to an H, so we can convert back and forth. Okay, and then I said we're going to add a KBP value definition. That's going to represent an actual item in our JSON schema, and then finally we're going to implement cons, and then concat in our KBP H list. Okay. So our interpreters will have to be, we'll have to have two methods now for our recursion. One for KBP H list and one for KBP value. And just quick how this would work with the location. Case class is you would build up the case class, the schema. You would then get your generic representation of it, and then finally you would wrap it all in your KBP convert class. And this is now our schema that we can run through an interpreter, and we'll see an example of that later. Okay, so now we can generate documentation, parse JSON, and generate JSON for any combination of H list, option, string, and double. All right, cool. All right, so let's talk about validation in the context of parsing JSON. There's kind of two things we can do. We can short circuit when we validate, which means if the error is wrong, we return. And that's going to be, for instance, if we're parsing data or we're converting data. For instance, if we require a name and it does not exist, there's no reason to continue on and verify that they're words only, or that they're max of 30 characters. So that would be short circuiting. But when we're in once we have our data, we can accumulate errors. Yeah, so we can accumulate errors at I don't know, right there. So, and then the other place we can accumulate errors is on each parallel input. So latitude, we can go down and validate latitude as far as we can. longitude as far as we can, and wherever there's an error, it will still try to convert each of the inputs. So even if there's an error converting latitude, we will still try to convert longitude and validate it as far down as possible. All right, so we can kind of think about validation in kind of the same terms that we were just using our schema. So we have this trait, this base trait, should probably be an abstract class, but it takes our type T, and then we can define validation operations. These are descriptions of validations. So this one is just saying, hey, this string, right, can have a max of whatever. Okay, and then we can provide interpreters which do both validation with. So for is valid, our return type is A to either an error, or we can just return the original type. And so for max length, we know the input's going to be a string. We then do the validation, and then for the documentation case, again, we're just returning a string here, and so then all we need to do is return a description of the data, maximum of max. Okay, and so if we go back to our interpreter, this is our string data. We can add validation operations to our case classes. You can do this as annotations as well, I believe. I think that's a little bit more of a functional approach, but you can do this as well. So you can see we have a list. There should be actually a list of validation operations. And so we can have as many as we want. So in our interpreter, and then if we look at our for comprehension, first we're going to try to find the key in the JSON. If we can't find the key, we short circuit. Then we're going to try to convert it to to a string. If it doesn't convert to a string, we short circuit, and then finally we arrive at the. We have a string. We pass it through all of our validations. If they pass all of our validations, we can return a right of the containing the string. If they don't pass the validations, we can return a left of string. And generally, don't use string for an error, but for this, I think we're good. Okay, so now we can do all the things we could before, and we can describe our data in terms of validation as well. All right, endpoints. So a REST endpoint is really just an input, an output, and an error. So let's kind of describe that as a GADT or similar. So this isn't really a GADT, but it's still a description of the data. And in each of these case classes, we have a reference to the description of the data we're expecting. So, for instance, for create, I is the type of value that we're going to expect as an input. So let's maintain a description of that. Same with error, and then same with output. Okay, and so if create is expecting those values for input, output, and error, we can do all that in the interpreter, and then the only thing that you really need to do in your business logic is to produce a function from I to either E or O. Okay, so that's, I think, fairly powerful. I don't know, pretty good. You can also do anything. So you can, if you have side effects, you can create a different interpreter that is expecting a function from I to IO of either those two values, or you can introduce 0 if you would like as well. Okay, so the REST schema interpreters, they're like, I think if you're a company, then you would provide a small number of interpreters as infrastructure, and they would provide these mechanisms. So they use interpreters to marshal and unmarshal data, to validate data. They're responsible for encoding the routes, which we'll see. They determine what to use as an ID. So we just produced data that didn't have an identifier in it, and there's really no reason to in the context of a REST API until you are, I don't know how to explain that now. That's all right. The interpreter should also provide roles for security and page limits and etc. All right. Hopefully that's all right. So the pseudo code for let's say HTTP4S. The first thing that we would do is we would define an array of byte interpreter that uses one of our JSON interpreters. All right, so we can go from an array of bytes, which is the request body, to JSON to some type A, and vice versa. So A to JSON to the output request. We would then create this function. I'm sorry. Extract request as an array of bytes, and then pass that to the interpreter. It would then call the business logic, which is your input types. So your whatever function you provided, your I to your either of E or L. It would then marshal the result or marshal the error, and then this is all encapsulated in HTTP route. Alrighty. And so Bones provides these interpreters at the moment. Our wire protocols, including protobuf, our documentation, including Swagger, and our protobuf definition files. There's kind of this proof of concept database generator, a React component, HTTP4 routes, Scala check generators, which is interesting to do with validation, because, for instance, if you are only expecting words, or if you're only expecting a length of 30, you can make sure you either generate valid data or you can actually generate invalid data. And right now, these are the data types that are supported. So Bones can build HTTP REST endpoints for any of the interpreters I provided, and any of these data types is what I could say if this was a finished product, but it is not. And I will now do a quick demo. Okay, so first we're defining our error schema. Oh, let me make that a little bigger. Oop, I think. Oh. All right. I guess I can't make it bigger. Is that all right? It's reasonable. All right, so we're defining our KBV error, which is just going to be a string in this case. We have our location, which is our Latin lawn, our waterfall. So then we create the schema for our location. You can see we're making sure that the latitude and longitude are between -180 and 80. So for our waterfall schema, we're saying it's a name. We have a max of 200. It must be trimmed. This is something that actually bit us on the enterprise software. They didn't trim their inputs. And this is also saying, hey, these needs to be words. The location now references the schema that we just defined, and then the height. Okay? And then, so that's our data definition right there. And so this second thing is our service operations. So what we're saying is, hey, create a path that's called waterfall. So for create, we're going to say the input is the waterfall schema, the output's waterfall schema, and then the error schema is the error schema. So we have a create, read, update, and delete endpoints for this. And so then we're going to use this interpreter, which does make some assumptions like localhost, et cetera, but generally it's taking most of those interpreters that we just talked about and combining them into a single interpreter. So this one returns the CRUD endpoints. This one produces the database schema, and then this one is going to produce a React. Okay, and that is running right now, so we can go ahead and open this up. Okay, so this first one is our protobuf output. You can see the waterfall and location are defined. This with ID thing is a little weird, but I talked about how the REST endpoint does have an ID, but not necessarily part of the base schema. So we actually add that on as part of the interpreter, not necessarily as your data description. So here's our schema. You can copy and paste this and put it in your database, or you could create an interpreter which does a diff on the database and updates it appropriately. So here we have our Swagger output, which isn't quite complete, but you can see at least it does give us our post, get, put, delete. And then it generates our waterfall and location definitions. I don't think you can also add the validations in there. I don't think I've quite gotten to that. And then finally, we have a React component, which worked reasonably well before, but for some reason the lat and long are not showing up at this point. So I can't really demo it, but this does allow all the CRUD. You can delete, edit, whatever. All right. And then finally, I wanted to show protobuf. So the first thing I'm going to do here, I'm just doing a curl request, and I'm saying, give me the content. Oh, I can actually make this bigger. So I'm specifying the content type of protobuf. So this is going to create a file. This is going to download the binary data. It's going to create a file called 1. We're going to encode that into base 64. And oops, I thought I saved that link, but let's see. can see that, oh, there it is. So there's the name, there's the, and then the other data types are there too. It provides create, read, update, and delete for protobuf as well. And that's all I got. So, do I have any questions? Cool. Thank you very much for sticking around and making it through my talk.